So this is ELC131, Circuit Analysis 1. And in this presentation, we're going to take a closer look at capacitors. Now, some of the capacitors that you will work with are considered or called non-polarized capacitors, meaning that they're somewhat like resistors. They have no polarity, and they can be installed in a circuit in any direction. So figure 1 shows the accepted US schematic symbols for capacitors, which really denotes that they're non-polarized capacitors. Now, the types of dielectrics that are used to construct non-polarized capacitors are mica, ceramic, mylar, polystyrene, and other dielectrics. But you notice looking in figure 2 at the capacitors in figure 2 that we see no positive or negative markings on the cases of the capacitors. So from this, we can infer that there is no polarity to these capacitors, that they can be inserted in the circuit in either direction. Now let's take a look at the markings that you'll see on capacitors. And the capacitor in figure 3 shows us the markings of 331J. And with this type of marking, the first two numbers are significant digits, the third number is a multiplier, and the letter denotes the tolerance of the capacitor. Now, the value of these capacitors is expressed in picofarads. So this capacitor would have a value of 330 picofarads, and the letter J denotes a plus or minus 5% tolerance. Now, notice the line under, or the underline under the numeric value, and this symbolizes that the capacitor has a maximum voltage rating of 50 volts. Well, let's look at another example, and the capacitor in figure 4 has the labeling of 103K. Again, the first two numbers are significant digits, the third number is the multiplier, and the letter K denotes the tolerance. And the value of these capacitors is always in picofarads. So this particular capacitor would have a value of 10,000 picofarads, which would be expressed as 0.01 microfarads. And the letter K denotes a plus or minus 10% tolerance in the capacitor. And there's no line under the numeric value, so that tells us that this capacitor has a maximum voltage of 500 volts. Now, some capacitors that you'll deal with are polarized, and that means they have specific or designated positive and negative terminals. Figure 5 shows us the US schematic symbol for a polarized capacitor, and figure 6 shows us two alternate schematic symbols for polarized capacitors. Now, with these capacitors, of course, you have to observe polarity. If you don't, the capacitor will not have the proper value of capacitance, and they will explode. So the types of polarized capacitors that you will encounter are electrolytic capacitors and tantalum capacitors. So let's take a look at the electrolytic capacitor. These capacitors are constructed by taking lengths of foil and separating them with tissue that's soaked in an electrolyte. And then these lengths of foil are rolled up so that they can place them inside of a case, such as we see in figure 8. Now, because of the construction of the capacitor and the tissue that's soaked in an electrolyte solution, a thin layer of aluminum oxide is created along the positive plate, and this results in a very large value of capacitance in a relatively small package. And again, what happens if you connect these backwards is that this aluminum oxide layer will not be correctly created, and it'll cause current to flow through the dielectric from plate to plate. And this current, of course, will cause a great power dissipation, and that power dissipation will result in the capacitor exploding. So referring to figure 8, we see an electrolytic capacitor, and on the case they denote the value 680 microfarads, the DC voltage rating 35 volts, and the polarity is denoted with negative signs inside the white stripe with arrows pointing to one of the leads. And generally speaking, as you note in figure 8, these capacitors have the negative terminal is the shorter of the two leads. So two things with these capacitors: again, you must observe polarity, but you also must observe the voltage rating. That if you exceed the 35 volt rating of this capacitor, it may explode. Now, the other type of polarized capacitor that you'll encounter is a tantalum capacitor. And the construction of these capacitors is that the anode terminal is connected to a layer of tantalum. Tantalum is just a metal. And then the dielectric is constructed with tantalum pentoxide, which is just a mixture of powdered tantalum and oxygen molecules. And what this does is creates an oxide layer between the anode and the dielectric, which allows us to have extremely large values of capacitance in a very small package. The capacitor we see in figure 9 has a value of 2.2 microfarads, a DC working value of 25 volts, and notice on the case the plus sign denotes the positive terminal. Again, these capacitors will explode if they're connected in the circuit incorrectly. Now, most of the surface mount capacitors that you will encounter are tantalum capacitors. So we can have, again, a large value of capacitance in a very small package size. Now, you'll also encounter variable capacitors. The schematic symbol for a variable capacitor is shown in figure 10. And this is similar to the schematic symbol used for variable resistors. And just like with a variable resistor, the variable capacitor allows us to manually change the value of capacitance. And this is done by changing the overlapping area of the plates of the capacitor. So looking at the variable capacitor in figure 11, you see that there's one set of plates that are stationary, and this is called the stator. There's another set of plates that are connected to the shaft, and this set of plates can rotate in between or interleaving with the stator plates. So rotating the shaft changes the overlapping area of the plates. And again, as I said in the previous presentation, that capacitance equals permittivity times area divided by distance. So by rotating the shaft, we change the overlapping area of the plates, thereby changing the value of capacitance. Now, this type of variable capacitor uses air for the dielectric. And this is the type of capacitor that's used to change stations in a radio receiver. So when you're turning the tuning knob on a radio, what you're doing is rotating the shaft of a variable capacitor. Now, another type of variable capacitor that you will encounter is called a trimmer. And these are similar to a trimmer potentiometer. These variable capacitors are more of a set it and forget it situation in that we adjust them once and then leave them alone, unlike the previous example where that variable capacitor is constantly changed to change radio stations. And again, the value of capacitance is changed by changing the overlapping area of the plates. Looking at the capacitor in figure 12, you can see that the plates are nearly half circles. So as you rotate the shaft with a screwdriver, you change the overlapping area of the plates. Now, with these types of capacitors, the dielectric can either be air or ceramic, depending upon the construction. And these types of capacitors are used to tune electronic equipment to precise frequencies for circuits such as oscillator and communications equipment such as radio transmitters. And this allows us, of course, to fine-tune circuits for very precise capacitance values. And these trimmer capacitors are only adjusted during the manufacturing of equipment or during the servicing of equipment. Now, one concept you need to be familiar with is the concept of dielectric resistance. Now, some current leaks from plate to plate through the dielectric. And to account for this in a circuit model, we need to show a path for this leakage current. And this path is denoted with a parallel resistor, RP. Now, in the painter text, he designates this resistor as RD, the dielectric resistance, but it's the same concept. Now, depending upon the dielectric material, this leakage current could be in the nanoamps, but with electrolytic capacitors, they can have leakage currents that range anywhere from 5 microamps to 20 microamps per microfarad. And also, this leakage current will increase with the age of the capacitor, because as electrolytic capacitors age, the electrolyte tends to dry out. And this leakage current also increases with temperature. Now, capacitors connected in series combine like resistors connected in parallel. Referring to the circuit of figure 14, we see a 22 microfarad capacitor connected in series with a 47 microfarad capacitor. These series capacitors combine, or we find the total capacitance of these two capacitors either using the product over sum formula or the reciprocal formula. So for figure 14, I can calculate the total capacitance by using the product over sum, C1 times C2 over C1 plus C2. So the total capacitance of this circuit is 15 microfarads. Now we connect capacitors in series to divide voltage, just like we connect resistors in series. And we do this commonly if the voltage applied exceeds the DC working voltage of a capacitor. We can connect two capacitors in series, thereby dividing that applied voltage up into pieces. Now, looking at the circuit of figure 14, we can calculate the voltage across one or both of these series capacitors. But we have to calculate it in the same manner as we calculated current through parallel resistors. So for the circuit of figure 14, we can calculate the voltage across C1 using the formula given. VC1 equals V source times C total over C1. And hopefully you remember the current divider equation for parallel resistors, where IR1 would be equal to I source times R total over R1. So the voltage across capacitor C1 is 6.7 volts. And I don't show the equation or the derivation, but if VC1 is 6.7 volts, then VC2 would have to be 3.3 volts because the applied voltage is 10 volts. So notice with these series capacitors that the smaller value capacitor has the larger voltage and the larger value capacitor has the smaller voltage. Again, VC1 is 22 microfarads, but it will have 6.7 volts across it. C2 is 47 microfarads, and it will have 3.3 volts across it. So there's an inverse relationship between the value of capacitance and the voltage across that capacitor when connected in series. Now, capacitors are also connected in parallel. Parallel capacitors combine like resistors in series. So for the circuit of figure 15, the total capacitance is equal to C1 plus C2. So the total capacitance for that circuit is 69 microfarads. And we connect capacitors in parallel so that we can increase the value of capacitance. So in this presentation, we looked at non-polarized capacitors and capacitor markings. We looked at polarized capacitors, electrolytic and tantalum capacitors. We looked at connecting capacitors in series to divide voltage, and we looked at connecting capacitors in parallel to increase capacitance.